Okay, in this video we're going to talk about sets of numbers. We're going to start from the most basic, the ones that humans invented first, which are called the natural numbers or sometimes the counting numbers. Okay, because these are the ones that people naturally, came across or invented, however you want to look at it, and they're the ones that we count with. So when you're counting things, you count like 1, 2, 3, 4, 5, and so on. So the set starts with 1 and goes up like that. Okay, so those are the natural numbers. Put one over there. Okay, then, as we progress, we realize we need an identity for, or a name for 0 because we needed something more than just nothing. And so that brings in the whole numbers, which is basically everything that we had before, plus the idea that 0 is an actual quantity. So we could actually count 0. So if I have 4 fish and I give you 4 fish, I now have 0 fish. All right, so it doesn't look like a huge difference between these two sets. And in fact, it's just the 0, but it does make a difference in what these two sets can do. So like if we're talking about, can I divide by this set of numbers? Can I divide by the natural numbers? Yes, I can. Can I divide by the whole numbers? 0 is going to be a problem. Okay, so I've got to be a little bit more careful. So there are things that these sets can do that are a little bit different, and that's why we keep the we still distinguish between the two of them. Okay, and then as we went on, we realized that we needed to be able to express negative numbers. So we needed to have -5, -4, -3, and so on, in addition to our 0, 1, 2, 3, 4, 5 concept. So when we added, we have all the positives, we have 0, we have all the negatives, that's going to give us the integers. Okay, so we write this as dot, 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 -1, let's say -2, -1, 0, 1, 2, dot, dot, dot. Okay, dot, dot, dot means continuing forever in that pattern, in that direction. Okay, so now we have all of the whole numbers, positive and negative. Okay, so still no fractions, no decimals, nothing like that, just the whole numbers, positive and negative. Okay, so we know on this side of the number line we have the positive numbers. And on this side of the number line, we have the negative numbers. Okay, the positive numbers are the same as natural. Okay, so that's another way to express those two things. Now we've got negative numbers on the other side. 0 is kind of a special case because it's not positive or negative, but we could lump these all together as non-negative. Okay, so if it's not negative, it's either 0 or positive, and that's another way to say the whole numbers. Okay, so we've got positive, negative, and non-negative, and that's going to include 0 in it. Okay, now let's expand this out to real numbers. Okay, so the book defines real numbers as all the points on these number lines. If you look, we've got lots of points, we've got infinitely many points, but we're missing a lot of numbers too because we have all this space in between these numbers that we're not accounting for. So what fills in those spaces? Well, the real numbers do. The real numbers make up the entire number line and vice versa. All right, so of the real numbers, we can break this into categories. So we can have rational and irrational. Okay, so rational, a little divider here. Hopefully I don't run out of space. Okay, rational is defined as all of the numbers in the form P over Q, where P and Q are integers. Okay, so they can be positive, they can be negative. You can even have 0, and can't have Q equal to 0, of course, because that's not defined. But we could have positive, negative, we could put 0 on the top. So we get all sorts of fractions like 2/3, 1.5, things like that. We also get other things that could be written in that form, but maybe don't exactly look like they're in that form. Okay, so we get all of these numbers over here because, of course, whole numbers, you could just put them over 1, over 1, over 1, over 1. That's the same thing, and that makes them all fractions. So our integers, whole numbers, natural numbers are all part of the rational family. Okay, so let's go ahead and put in integers, whole, and natural here. Okay, they're all part of this family. And actually, let me hold off on writing those. We'll just give some examples right here, and then we'll write some. Okay, so we could have like -1, +2, +10. Okay, so we've got integers, whole numbers. We've even got 0 to make the whole numbers. We also have things like 3/4. Okay, that's a rational number, definitely in fraction form. We also get things like 10.2. Okay, that's not a fraction, but we could make it a fraction. Remember, you can take any decimal and put it over 10, 100, or 1,000. So this is the same as 10 and 2/10 or 1/5. So we could write that as a fraction, so it's rational. We can also take things that have, so this is a terminating decimal, one that ends. We could also take things like 15.232323. Okay, we can see that that's in a repeating pattern. We can also write it as 15.23 bar. Okay, those can also be put into a fraction. So we call this a terminating decimal. We call this a repeating decimal. Those also fall under the rational numbers. Okay, irrational is going to be everything that's left over. Okay, so basically it's going to be things that can be written as non-repeating, non-terminating decimals. Okay, so anything in this category, if you try to write it as a decimal, it's going to be a non-repeating, non-terminating decimal. So it's going to go on forever without any sort of pattern. So pi is one example that you're probably familiar with. We usually write it as 3.14, but really it goes on forever and it doesn't repeat. Things like the square root of 2, the square roots that you can't evaluate, those, when you put them into a calculator, you'll see that they are non-repeating, non-terminating decimals. Okay, so like square root of 7, square root of 21, all of those are going to be irrational. Now, if you have one that you can evaluate, like square root of 25, that is going to be on the rational side, because if you can evaluate it, it's going to be a whole number, and a whole number is on the rational side. Okay, so all of the real numbers either split into rational or irrational. Now, irrational, we really can't break down any further than that, but rational we can. So let's take a look at that. Okay, so I rewrote what we have going on over here without the example, so we have a little bit more space. So the reals break up as rational and irrational. Irrational is really not going to break down any more than that in terms of what we need to do. So let's look at the rational. Okay, so for rational, we can break this up as non-integers and integers. Okay, and that's going to cover all of the rational numbers. So we're breaking off the integers like -5, -2, 0, 10, things like that. We're going to break off the integers. The non-integers is basically going to be everything that's left over. So fractions, decimals, terminating decimals, repeating decimals, things like that are all going to get lumped into the non-integer category. Okay, so the non-integers really aren't going to break down anymore for what we're looking at, but the integers do. Okay, so this is where we look at the ones that we saw before. We saw that integers we could split up as negative and non-negative. And we had another name for the non-negative. Remember what that was? That was the whole numbers. Okay, so we break it into the negative integers and the non-negative integers. Okay, I need to write integers here because I don't mean all the numbers, just the integers. So the negative integers are things like -2, -3, -5. The non-negative integers are 0, 1, 2, 3, 4, 5. That's the whole numbers. And then we can break up the whole numbers again. If we split off 0, then the rest is going to be 1, 2, 3, 4, 5, 6, 7. It's going to be the positive integers. And of course, that's the same as the natural or counting numbers. Okay, so here's the breakdown of all of the groups that we have so far. Okay, so let's talk about subsets Subset means that it's contained in another set, and it's the symbol like a kind of like a backwards or no forward C with a little line underneath it. Okay, so one is a subset of another if it's contained in it. So we could say irrational is a subset of the reals. Okay, we could say that the natural numbers is a subset of the integers. Okay, so come over to our chart. If you're not sure, all right, we've got natural numbers down here. And look, they are a part of the integers. The integers broke up into all these pieces. All of the things below integers are part of the integers. So the natural numbers are a subset of the integers. Okay, could I say that the whole numbers are a subset of irrational? Are the whole numbers a subset of irrational? Well, here's whole numbers. Are they part of irrational? No, they're on a completely different branch. I can't get to irrational from the whole numbers. Irrational is over here. So whole numbers and irrational numbers don't have anything in common, so they are not a subset. I would put a strike through that. Whole numbers are not a subset of the irrational numbers. Okay, could I say that the integers are a subset of the whole numbers? Are integers a subset of whole? Okay, so come over here. They're on the same branch. They're definitely related. But are the integers a subset of the whole? Are integers part of the whole? No, integers are bigger. There's more to the whole. There's more to the integers than there are to whole. So integers are not part of the whole. They're bigger than it. So integers are not a subset of whole. But we could say that the whole numbers are a subset of integers. Okay, because whole numbers are part of the integers. Okay, so that's the idea for subset, is you want that set contained completely in the other set.